41st lecture on response of linear systems to random inputs. We shall confine to LTI systems and systems which are BIBO, that is bounded input, bounded output, stable. What does this mean? This means that HT mod dt minus infinity to plus infinity shall be what? Finite, less than infinity. This is the kind of systems that we talk about in our discussion on response of linear systems to random inputs. So you have a random input x of t. The system is described by an impulse response h of t, and you are interested in y of t. Naturally, since x of t is random, x of t has only probabilistic or statistical descriptions. It has nothing else, and therefore it is reasonable to expect that y of t shall also have only probabilistic and or statistical descriptions, and therefore what we shall do is to characterize y of t given the characteristics of x of t and given h of t. This is our purpose of discussion, and in the process naturally x of t shall be described by its mean value, by its mean squared value. It could be described by its autocorrelation function. It could be described by its spectral density. All right, and y of t shall also have the same kind of description, except for the fact that we might want to correlate y and x, and therefore two other correlation coefficients, cross correlation coefficients Rxy and Ryx shall be of interest, and also the corresponding spectral densities, that is the Fourier transforms of the cross spectral densities. This is what we wish to establish, and as we have done in the past, we always start with the time domain, then go to the frequency domain. So let's start first our consideration about the time domain. Now you know that in the time domain, given a system with an impulse response of h of t, in the time domain the output is the convolution of input and the unit impulse response. So it is of the form x t minus lambda h lambda d lambda. We could also have taken the other equivalent form, that is minus infinity to infinity x of lambda h of t minus lambda d lambda. Well, I find it a little more convenient to use this form in the context of random signals. So we shall stick to this. Suppose we want to find out the mean value of the output process. Mean value is naturally the expectation of this quantity, and the expectation operator and the integration operator can be interchanged, and therefore it is simply minus infinity to infinity e of x of t minus lambda h lambda d lambda. And if the process is stationary, then this is equal to, is that required? Stationary process, stationarity of process. What I am going to do is to equate this to x bar. Is that required for stationary? Yes. It is required. Okay. So this for a stationary random process, therefore y bar equal to x bar multiplied by an integral minus infinity to infinity h lambda d lambda. Now you recall that that if we had multiplied the integrand by e to the minus st, then what would have this become? This would have become capital H of s, that is the system function or the transfer function. Lambda. Okay. If we had multiplied this by e to the minus s lambda, then this would have become h of s. And since e to the minus s lambda is not there, the way to get rid of this is to put s equal to 0. Then it becomes unity. And therefore, we proved that y bar equals to x bar multiplied by h of 0. Alright. h of 0, that is the system function evaluated at DC. S equal to 0 corresponds to direct current or direct voltage, and therefore the frequency is 0. And in that sense, h of 0 therefore is the ratio of the mean value of y to the mean value of x. This mean is over an ensemble, and therefore h of 0 is sometimes called the DC gain, because y bar and x bar, they are averages. The ratio of the two averages is the DC gain. Slightly loose terminology, but the terminology has gone, because one DC gain means it refers to frequency, whereas the averages are over ensembles. They may or may not be equal to time averages. All right. So we proved that the output random process has a mean value which is equal to input random process multiplied by h of 0. As an example, suppose we have a simple RC network. Okay, then what is h of s for this? 1 by s c r plus 1. Very easy to show, which I can write as 1 over CR divided by S plus 1 over CR. I am putting the pole in evidence and if I put 1 by CR, if I use a symbol, this is equal to B, small b, then H of S is equal to B divided by S plus B, and naturally H of 0 is equal to 1, which is also obvious from the circuit. At DC, the response is equal to 1, and therefore for this circuit, y bar equal to x bar. That is, the output mean value is equal to the input mean value. You can you can do this, you can verify this in the time domain. What is h of t for this? H of t is equal to 1 by, is equal to b by b s plus b, and therefore h of t shall be b e to the power minus bt times ut. That's correct. And if you substitute this in the integral, that is minus infinity to infinity h lambda d lambda, you shall precisely get this equal to x bar. You can verify this by putting in the integral formula also. Suppose you want to find out the mean squared value. We shall write this as the expected value of yt multiplied by yt. All right, a trivial manipulation, but we shall write this yt's twice. That is, we will write this as minus infinity to infinity x of t minus lambda 1. We shall use two variables, h of lambda 1 d lambda 1, and I will multiply this by minus infinity to infinity x of t minus lambda 2 h of lambda 2 d lambda 2. All right. You can ask me why I am doing this. I am going to find out in terms of the autocorrelation function. If we had used lambda 1 and lambda 2 is the same, well, it does not bring the autocorrelation function into evidence. Now what I do is I play the usual trick, that is I interchange the expectation and the integration operators. There are two integrals here, and therefore I have to be careful. I integrate last with respect to lambda 1 and first with respect to lambda 2, and I take the expectation operator inside, that is e of x t minus lambda 1 x t minus lambda 2 multiplied by h lambda 1 h lambda 2 d lambda 2. Is that okay? Have I missed anything? No. Now you notice that this is simply the autocorrelation function, that is Rx of or lambda 2 minus lambda 1, because the autocorrelation function is an even function, and therefore I can write this relationship as y squared bar is equal to minus infinity to infinity d lambda 1 minus infinity to infinity Rx lambda 2 minus lambda 1 h lambda 1 h lambda 2 to d lambda 2. This is the general relationship between the mean squared value and the autocorrelation function Rx lambda 2 minus lambda 1. You must understand that y and x are two different processes. What we are doing therefore is to express the mean squared value of one process in terms of the autocorrelation function of the other process. The other process is undergoing a transformation in the LTI system, which is reflected in the product h lambda 1, h lambda 2. So it is it cannot be simplified further, unfortunately, except for very special cases. Let's look at the special cases. Suppose the input process is white noise. If it is white noise, then what is Rx of, well, white noise means Sx omega, the spectral density, is equal to a constant, let's say S naught. And therefore Rx of tau, the autocorrelation function, is simply a delta function, S naught delta tau. Alright. If I substitute this here, then you can see that y squared bar equal to minus infinity to infinity d lambda 1, S naught I can take out, then minus infinity to infinity delta lambda 2 minus lambda 1, h lambda 1, h lambda 2, d lambda 2. This integral exists only for lambda 2, lambda 2 is the variable, only for lambda 2 equal to lambda 1, and under that condition the integral of delta lambda 2 minus lambda 1 d lambda 2 shall be equal to unity, and therefore if we carry this out, if we recognize this fact, the property, basic property of the unit impulse function, then we find that y squared bar equal to S naught minus infinity to infinity d lambda 1, then what shall we have? H lambda 1 and h lambda 1, because lambda 2 is equal to lambda 1, and therefore this is S naught integral minus infinity to infinity h lambda whole squared d lambda. Now we can get rid of the subscript 1, which means that the output mean squared value is equal to the input spectral density, which just only in the case of white noise, no, in no other case, multiplied by, this is simply the area under the HT versus T curve. Pardon me? HT whole square, that is, square of the impulse response. Okay. As an example, let's take the usual RC network. Let's take the RC network once again. This is XT, this is YT. We are not showing a plus minus. Why not? In the drawing of a circuit with excitation, we always show the direction of the current and the polarity of the voltage. Why aren't you showing this? Because they are what? Random processes. All right. They are random processes. All right. Pardon me?
So still we'll have to take a particular direction as a standard.
No, we don't. That's why we work in terms of. It's not important because we will always take averages, and therefore the polarity is not important. And we shall always work in terms of h of s, which does not require a polarity. All right, it doesn't require. It's a transfer function. So h of t here is b e to the minus bt ut, and therefore if x of t has a spectral density equal to S naught, that is, if the input is a white noise process, then the output mean squared value shall be S naught integral b squared e to the minus 2b lambda d lambda and the integral limits shall be from 0 to infinity. 0 because there is a multiplication by u of t. And if you carry out this integral, the result is b s naught divided by 2. Alright. Now, we want to interpret this result, that is mean squared value is equal to b s naught by 2 in terms of one more fundamental quantity, which is the bandwidth of the system. This system, this circuit R and C, the half power bandwidth, that is the 3 dB bandwidth, is simply 1 over, yes, what is the bandwidth? At what frequency will the voltage at the output be 1 by root 2 times the voltage at the input? What frequency? Isn't that obvious? B by S plus B. So for sinusoidal excitation, B by B plus j omega. When shall it be B by root 2? Magnitude. Omega equal to B. As simple as that. Alright? And pardon me? This will happen at omega equal to B. And therefore, the bandwidth of the system, bandwidth is defined as this. This is the DC response, let us say B, DC response is 1, and this is 1 by root 2. This is the bandwidth, and bandwidth usually is expressed in hertz, alright, so it is in hertz. What is the bandwidth then? 1 by 2 pi RC, hertz. Okay, this is the bandwidth. And we have proved that our y squared bar is equal to b s naught divided by 2.
Sir, omega is equal to b, the value is 1 by under root 2.
Yes, thank you so much. That's correct. 1 by root 2, not b by root 2. Alright. I stand corrected. Now, I want to interpret this result in terms of bandwidth. You notice that capital B, the bandwidth, can be written as B by 2 pi. So, isn't this equal to B by 2 is pi times B times S naught, pi B S naught. It's a result of fundamental importance, although illustrated with the help of a very simple example. Most of the communication channels in practice are low-pass systems, and most of the communication channels qualitatively at least follow the same pattern as the simple RC network. The ionosphere, for example, or the stratosphere, or duct propagation, microwave, they are all low-pass systems. That is, there is an upper cutoff frequency. Now, what it shows is that the mean squared value of the output process is proportional to the bandwidth. And this is why if you make a wideband system, you also get prepared to accept wideband noise. Alright? The output process, the output mean squared value is proportional to the bandwidth, and therefore the signal to noise ratio becomes extremely important. And this is why narrowband systems are employed. Wideband systems are very costly. This is a general principle useful in almost all communication systems. Let's look at, we have looked at the output mean value, the output mean squared value, and if you know the mean squared value and the mean value, you can of course find sigma y squared, which is equal to y squared bar minus y bar squared. Let's look at next the autocorrelation function, that is R y of tau, the third statistical description of the output process. Well, by definition, this is the expected value of yt and let's say yt plus tau. We can go through the same steps as we did for finding the y squared bar, and I'll simply indicate how this is done. We write y of t as minus infinity to infinity x of t minus lambda 1 h lambda 1 d lambda 1, and we write yt plus lambda as minus infinity to infinity x of t plus tau minus lambda 2 h lambda 2 d lambda 2. And we do the same trick, that is, we first write, I will not repeat these steps, we first write integral with respect to lambda 1, d lambda 1, and then integral with respect to lambda 2, take the expectation operation inside, that is expectation of xt minus lambda 1 times xt plus tau minus lambda 2, which shall give me an autocorrelation of the input function, autocorrelation of x, then you have h lambda 1, h lambda 2, d lambda 2. If you do this, then the ultimate value, I skip the algebra, the final value I get is ry tau equals to, once again it cannot be simplified further, d lambda 1 minus infinity to infinity rx lambda 2 minus lambda 1 minus tau h lambda 1 h lambda 2 d lambda 2. This is the final result. All right, this is ry tau. Now you also know the relationship between the mean squared value and the autocorrelation function. We know that if our derivation has been correct, then putting tau equal to 0, I should get y squared bar. Don't you see that this is indeed true? If I recall, what was my y squared bar? Here, y squared bar was, I beg your pardon, this is the relationship. Y squared bar was integral d lambda 1 rx lambda 2 minus lambda 1 h lambda 1 lambda 2, no, this sign is not there, multiplied by d lambda 2, and this is precisely what we have got here. If you put tau equal to 0, this is precisely y squared bar, and therefore my derivation is correct. It should not be different. And unfortunately, this relationship cannot be simplified further unless you know a specific shape or specific value of the autocorrelation function. Suppose the input is a white noise process, that is, suppose Sx omega is equal to S naught. You see the importance of white noise now. White noise is a concept, is a hypothetical quantity like Superman. But it is useful. It is useful. Superman is our topmost. I mean, we can compare Vijendra with Superman, and you know how how much distance is there. Similarly, white noise, we shall always judge what the deviation from white noise is. But white noise is a very convenient quantity to judge the process, the autocorrelation or the cross correlation, and so on. Now, if Sx omega is S naught, then Rx tau is equal to S naught delta tau, and if you substitute this here and utilize the property of the delta function, then I can again skip the algebra and we can show that Ry tau is equal to S naught, it's very easy, minus infinity to infinity. What shall we get? We shall get h lambda 1. H lambda 1 shall be there. Instead of lambda 2, we shall have lambda 1 plus tau. Now, this is an extremely interesting relationship. What does it show? What is this quantity? It's a convolution? No, it's not a convolution. In the time domain, it's not in the ensemble. It's not, the correlation is not calculated about the answer. It is the time average of h lambda 1 and h lambda 1 plus tau. In other words, this shall be proportional to Rh of tau. Is that clear? It's a very interesting relationship, that ensemble average of the output process, the autocorrelation, is proportional to the time autocorrelation of the function h of t. Yeah.
When you take time average, you take it from minus t to plus t and you divide by 2t and take the limit.
Yeah. So I have not taken that limit. All right. You replace this by capital T and minus capital T and plus capital
So
T.
still there is that 2t term.
I know. It's proportional. That's why I said it's proportional. I can divide by 2t. H lambda, after all, I mean, if I integrate this, it will be a finite quantity. It will be a finite quantity. I divide by 2 infinity, then the result is 0. That's a different thing. But suppose h lambda is a finite quantity, it exists over a finite interval, which I can take. What is h lambda? It is b e to the minus b lambda u lambda. All right. So it falls exponentially, and I cut it off at some place. Then I take the average. All right. The result will be slightly inaccurate, but if I take this sufficiently large, it will be sufficiently accurate for practical purposes. All right. The important point is that it is Ry tau is qualitatively at least proportional to a time average, which is surprising. Okay, it's a surprising result and an interesting result too. Once again, if I take the simple RC network, once again, in which h lambda is equal to b e to the minus b lambda u lambda, then, and the input process is white, then Ry tau is equal to S naught. Now, instead of minus infinity to plus infinity, we shall have 0 to infinity. H lambda 1, so it would be b squared e to the minus b lambda 1 e to the minus b lambda 1 plus tau d lambda 1. And if you clear the algebra, if you simplify this, you simply get b s naught divided by 2 e to the minus b tau, where obviously we have assumed that tau is, have we assumed tau?
No.
We haven't.
Tau need not be positive, that's what.
Tau need not be positive.
Yes, sir.
Okay, but is this result true for tau positive as well as negative?
Yes, sir. It's true for any term.
It cannot be. There is a contradiction. Because if tau tends to infinity, the autocorrelation should be 0. It's an exponential process after all, and therefore
So, sir, b is positive, it will be 0.
b is positive.
It will tend to,
No, but for tau minus infinity,
even then it will tend to small.
no.
Absolute value of the.
I will, but I am trying to justify. He says b is positive, okay, b greater than 0. If tau is minus infinity, then this is e to the power b infinity, which goes to infinity. This is not possible, and therefore this is true for tau greater than 0. If you put any tau, then obviously the modification, all the modification that you need is minus beta. This is the correct result. This is the correct result. Now,
Sir, it doesn't come directly from the derivations of modulus.
It does.
of tau.
Sir, how do you get 0 to infinity over there? It should be 0 to tau, because there are ut, 2 times ut functions. It will be a great function.
all right, let's go back. H lambda is equal to b e to the minus b lambda u lambda. All right, and Ry tau is equal to S naught. We'll put the integral limits later. S naught b squared e to the minus b lambda 1 u lambda 1. All right, then e to the minus b lambda 1 plus tau
Plus tau, sir.
plus tau
U of lambda 1 plus tau.
u of. Now do you understand why tau cannot be negative?
So it
Sir, it can be negative. Now we'll get
It
more
can be
tau.
negative, but you have to change the integral limits. Okay?
limits now are 0 to infinity.
Right.
Like 0 to tau if tau is
इस वक्त
positive.
इस वक्त we have
No, but you have to go from minus tau to infinity, where we have assumed that tau is greater than 0. Anyway, you can clear this mess. What I have shown is that Ry tau for the simple RC network is b s naught by 2 e to the minus b mod tau. Now let's be a little bit more realistic. Let's modify the input to be not quite white noise. Let's say we have the same network RNC. We have the same network RNC, but the input process Sx omega is not equal to S naught, but it is of the form, it is a low pass form. In other words, it is maximum value at DC and then it goes down. Well, what is the autocorrelation function for such a process? If I have something like this, Sx of omega, which goes down on both sides, well, one of the autocorrelation functions is of the form beta S naught by 2. I have chosen the constant intentionally, e to the minus beta tau. If this is the autocorrelation, then the spectral density is given by beta squared S naught. We have already done this example, okay, in spectral density. Beta square S naught by omega square plus beta square. Let us suppose that the input noise process is not white. It has the input noise process has an autocorrelation function like this, whose spectral density is like this. And you notice that when omega tends to 0, what does Sx omega tend to? It tends to S naught. And therefore, as far as low frequencies are concerned, if we confine ourselves to a low frequency band, obviously the process is approximately white. Well, you can define a bandwidth. You can define that it is approximately a white noise process from 0 to some frequency. That frequency, how will you determine this frequency? If we stick to half power definition, then it will be from omega equal to 0 to that frequency where the value becomes 1 by root 2 or something else. Spectral density. What is the unit of spectral density? Power per unit hertz, and therefore power shall be half, and therefore the bandwidth, if you are at all defining a bandwidth, it shall be from DC to a value of frequency at which Sx omega becomes exactly equal to half. Not half, S naught by 2. This is the true half power frequency. And I wanted to bring this out because it is not 1 by root 2. You must understand that this has the dimensions of volt squared or ampere squared, and therefore it shall be half. Now, what we establish is that at low frequencies, the input process is approximately white. Well, if it is so, then what is the output process? If I substitute this in the expression, what was my expression? D lambda 1, you have to tell me the limits. Rx lambda 2 minus lambda 1 minus tau, h lambda 1, well, in general my limits were minus infinity to infinity, minus infinity to infinity, then h lambda 2, d lambda 2. This was my general formula, alright. Now in this particular case, we have to integrate this quantity, Rx, multiplied by h lambda 1, h lambda 2. Now Rx of tau is like this. This is Rx of tau, and this is tau. This is tau equal to 0. What would be Rx of lambda 2 minus lambda 1 minus tau? Obviously it would be shifted to the right. Suppose I plot Rx of lambda 2 minus lambda 1 minus tau. What shall I plot it versus? What is it of interest? my integration variable is lambda 2, and therefore I should plot this versus lambda 2. If I plot versus lambda 2, obviously the maximum shall be shifted either to the right or to the left, depending on the values lambda 1 plus tau. So if lambda 1 plus tau is positive, then it would be something like this. Okay, this shall be lambda 1 plus tau. Is the point clear? The maximum shall occur at lambda 1 plus tau when the argument is 0. Alright, and therefore the range of integration, what will be the range of integration now? If we go back here, what will be the range of integration now? You look at this and look at this function. What is our network? Our network is a simple RC network whose impulse response exists only for t greater than or equal to 0, and therefore the lower limit of this shall become 0. The upper limit is still infinity. And is the point clear?
So if tau is negative, then the lower limit will
We are considering tau is positive. Okay. Finally, I will put a mod tau. I don't have to derive for tau positive as well as negative, because Ry tau is an even function. All right. This is some saving grace for the complicated calculation, if you consider it complicated. Now let's go back. You understand that this limit shall now be 0 to infinity because of h lambda 2, not because of anything else. And if it is 0 to infinity, obviously it shall have two ranges. One is 0 to lambda 1 plus tau, and the other is lambda 1 plus tau to infinity. Alright, so this integral therefore can now be broken up into two parts, that is Ry tau shall be equal to 0 to infinity d lambda 1 multiplied by 0 to lambda 1 plus tau, whatever the integrand is, plus 0 to infinity d lambda 2, then lambda 1 plus tau to infinity. Okay? Whatever the integrand was, is the same integrand. Why did we have to divide into two parts? Because in the two ranges the function is different, and therefore we must take care of that. Now if you substitute this and clear the algebra, then the final result that you get, which I want you to look at very carefully, is b squared beta s naught divided by 2 b squared minus beta squared e to the minus beta tau minus beta by b e to the minus b tau. This is the final result that you get after carrying out the integration. Now because Ry tau is an even function, we take care of both positive and negative tau by taking a mod sign there. I want you to notice that if beta tends to infinity, well, what was your Sx of omega? You recall? What was it?
Beta square.
Beta square S naught divided by omega square plus beta square. If beta tends to infinity, then what does Sx omega tend to? Obviously S naught. Alright? It also tends to S naught as omega tends to 0. But let's suppose beta tends to infinity, then Sx omega, that is the input noise process, tends to white noise. If beta tends to infinity, then what does this tend to? If beta tends to infinity?
0.
Well, this tends to 0. No, it doesn't.
No,
Because of this factor, beta by b, it becomes b s naught divided by 2. Beta tends to infinity, so you can ignore b squared, minus 2b squared, then minus, there's a beta here, there's a beta here, so these two betas cancel. It becomes b s naught by 2 e to the minus b mod tau. That's what it becomes. Now isn't this precisely the result that we had obtained in the first example, when we had considered the RC network to be fed by a white noise process? The output autocorrelation was precisely this. Alright? Which means that it's not too bad an assumption, white noise. It does give an idea of the autocorrelation. The other thing I want you to notice is, what is beta tends to infinity in practice? Obviously, you cannot get white noise, you cannot get beta tends to infinity, but it's always relative. When you say x is much greater than y in electronics, 1 is to, what does the ratio stand for?
100.
1 is to 100. Or you haven't done analog circuits here, analog electronic circuit, no? No. 1 is to 10 is good enough for us, alright, for electronics. 1 is to 10. X is to y equal to 1 is to 10, then you say x is much greater than y, alright? It works in practice. Here, what is the approximation then? For the input noise to behave like a white noise, what is the approximation? Obviously, beta, there should be relationship between beta and the system function, system parameter. What is the system parameter? B, beta and B, and therefore beta much greater than B will make sure that the input behaves like a noise, behaves like a white noise, and the output autocorrelation function is this, that is B S naught by 2. You can arrange this function in such a form that beta much greater than B, you get Ry tau of this form. I shall simply write the expression. You get B S naught by 2 e to the minus B tau, which is the SEF, autocorrelation function for white noise. And then this is multiplied, this is modified by a term which tends to unity as beta becomes much greater than B. And this term is 1 minus B squared by beta squared multiplied by 1 minus B by beta e to the minus beta minus B times mod tau. You can see from here that when beta becomes much greater than B, it is simply the white noise autocorrelation that you finally get. This would be a good point to stop. Tomorrow, which is the last class, we shall consider cross correlation. That is correlation between, we have done y bar, we have done y squared bar, we have done the autocorrelation Ry tau. The only time domain quantity that remains is the cross correlation function. That's what we shall calculate, and we shall have a glimpse at the frequency domain analysis.